In this video, we solve problem 9.2.031 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the sum of the convergent series. We have this, and they give us a little box, and we're supposed to enter our answer there. Well, if we're asked to find the sum of a series, there are really only two types of series that we can find a sum for using the ideas discussed in Calculus 2. And they are these. If we have a geometric series, that is a series that can be written in the form, the sum as n goes from 0 to infinity of a times r to the n. If we can write the series in this form, so that when n is equal to 0, we get a, when n is equal to 1, we get a times r, and then every time as we go from term to term, we just multiply by another r. If the series, when expanded, follows this pattern, the sum of the series will be the first term, which we're labeling a, over 1 minus the common ratio, whenever the absolute value of r is less than 1. This series will always converge to that number under those circumstances. Otherwise, the series diverges. So that's one where we know the sum of the series. We have a formula for it, but that's not actually what we have here. This is not a constant times a constant raised to the n, and there's no way I can use algebraic manipulation to make this expression look like a constant times a constant raised to the n. These are numbers, and we're taking that number and we're multiplying by an extra number every time. We're taking this term and we're multiplying by an extra r every time to get from term to term. That's not what's happening here. Here we've got a polynomial involving n in the denominator and a constant 4 in the numerator. Now there's another series that we can find the sum of, and that's called a telescoping series. Now, what makes a series a telescoping series is that it can be written in this form. You're going to start with some value of n. I'm just going to use n equals 1, but it could be a different value of n. That would be fine. If it can be written as some function of n minus some function of n plus k, then if we expand this, like when n equals 1, let's say that k is equal to 1, we'd have f of 1 minus f of 2. When n is equal to 2, we'd have f of 2 minus f of 3. What we would end up with is a sum of terms, and a lot of them are going to cancel because this expression looks just like this expression. This expression is just sort of k units ahead, like we're putting a value that's k units larger than this guy. So if this is just 1 unit larger than this guy, if this is an n and an n plus 1, if this is 2, that's 3. And if that's 3, that's 4. If that's 4, that's 5. And because we've got the opposite signs, because we'd have an f of 3 in one expression and a negative f of 3 in another expression, those would end up canceling. So if the series can be written in this form, I'm using k equals 1 just for example, but it doesn't have to be k equals 1, then this series can be found, or the sum of the series can be found by finding the nth partial sum. For a telescoping series, S sub n, after simplification, S sub n will have a finite number of terms. Well, and they always have a finite number of terms. They always have at most n terms, if we're thinking of this as the nth term. But it's going to be the same, let me see, it's going to be the same number of terms generally every time. So for maybe n greater than or equal to 3, all the S sub n's might have 5 terms, or all the S sub n's might have 3 terms. So S sub n will have let's just say a specific number of terms for lack of a better word. Once you have that expression for S sub n with that specific number of terms, you'll be able to compute its limit. And that will be the sum of the series if that limit exists. And I'm going to call this A sub n. That's going to be the sum as n goes from whatever that starting number is. I'll just say 1 to infinity. That's what we're looking at with a telescoping series. Now, this is definitely not this. And it initially does not look like this, but notice you've got an n and an n plus 2 in that denominator. If we use partial fraction decomposition to rewrite that, we can rewrite that as a sum or possibly a difference of two terms. Because there's an n and an n plus 2, we're going to have an f of n and an f of n plus 2. So that's going to be the approach. We'll use partial fraction decomposition first to rewrite this in this form, and then we will use that expression to find a pattern for S sub n, and we'll take its limit as n goes to infinity to find the sum of the series. Okay, so that's the plan. Let's do the partial fraction decomposition for this. We'll keep going. So we have 4 over n times n plus 2, and n plus 2 are linear factors. So this can be written as a over n plus b over n plus 2 for the right values of a and b. In order to find a and b, one way we can do that is we can take this equation and multiply by the least common denominator, which is just the original denominator. It always is. Then these guys reduce, the n's reduce here, and the n plus 2's reduce here. And what we end up with is a 4 equals a times the quantity n plus 2 plus b times n. Now I know we're tending to think of n as an integer, a positive integer starting at n equals 1 because of the problem statement. But when we're solving this equation for a and b, we can just treat n as a real number. So we're just trying to find the values of a and b that would cause this expression to be equal, or this expression on the right to be equal to the expression on the left. One way we can find that is by setting n equal to the values of n that would cause each of these factors to be 0. So n plus 2 is equal to 0 when n is equal to -2. So I'd have 4 over here if I substitute in -2 equals a times -2 plus 2, which is a times 0, which is 0, plus b times n, which is -2. And then if we divide both sides by -2, we get b equals -2. And then to make this 0, obviously n would be 0. So if n is 0, we have 4 equals 2 times a. So a is equal to 4 divided by 2. And 4 divided by 2 is 2. So this is telling us that our original nth term of our series is equal to a over n, where n is equal to 2, plus b, which is -2, over n plus 2. And adding -2 is the same as subtracting that. So our series can be written in this way. It's the sum as n goes from 1 to infinity of this, which is equal to this. So we're just going to substitute this in. And then we see that form that I mentioned. There's my f of n, and there's my f of n plus 2. Now, I was telling you that some of the terms will cancel. Let's actually see that in action here. When n is equal to 1, if this is my a sub n, a sub 1 is going to look like this. We'll have 2 over 1 minus 2 over 1 plus 2. So when n is 1, we have a 1 here, and 1 plus 2 is 3. That's our first a sub n. It's our a sub 1. And then for a sub 2, we substitute in n equals 2. So we'll have a 2 in that denominator, and 2 plus 2 is 4 in this denominator. Now we could simplify these, but I don't recommend it. We're trying to see what cancels. And everything, you're going to be able to see the pattern a little bit easier if you leave everything expanded, if you leave everything in this original form. when n is equal to 3, we're going to have a 2 over 3, and 3 plus 2 is 5. When n is equal to 4, we'll have 2 over 4 minus 2 over 4 plus 2, which is 6, and so on. And you keep going forever. Now this is what I was talking about with the cancellations. Notice that we've got a negative 2/3 here and a positive 2/3 there, so those are gone. And notice that we have, oops, it's a minus. We have a negative 2 over 4 here and a positive 2 over 4 there. Those are gone. And if we continue, let's do one more term for n equals 5. We'd have a 5 in this denominator because that's our n. And then this denominator is 5 plus 2, so 7. If we continue in this way, notice what happens. I have the negative 2/5 and the positive 2/5, and those undo each other. Those are gone. They cancel each other out. So when we do this, we end up with a finite number of terms. On the next one, when n equals 6, we're going to have a positive 2 over 6, and that negative 2 over 6 will cancel. And then the one after that, we're going to have a positive 2 over 7 to cancel with the negative 2 over 7, and those will cancel. So that's what I meant when I said that the partial sums will have a finite number of terms. They always have a finite number of terms because n is always finite. But we're going to have a specific number of terms for s sub n when n is greater than some value. So let me just expand that in this case. S sub 1 is just a sub 1. So that's going to be 2 minus the 2/3. S sub 2 is a sub 1 plus a sub 2, which is the 2 minus the 2/3. And actually, I think I will simplify that one, plus 1 minus the 2 over 4. I think I'll leave that one alone. Still no cancellations yet. With S sub 3, though, this is what we have. We've got the 2 minus 2/3 plus 1 minus 2/4. And then with a sub 3, we have the 2/3, positive 2/3 minus 2/5. And that's where we start to see some of those cancellations. So notice we have 1, 2, 3, 4 terms there if we drop the parentheses. If we drop the parentheses here, we can think of this as 1, 2, 3, 4 terms as well. So I think we're going to have 4 terms every time. Let's see. Let's see if the pattern continues. So I'm just rewriting a sub 1, a sub 2, and a sub 3. Because S sub 4 is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. And then I'm tacking on a sub 4. When n is equal to 4, we have 2 over 4 minus 2 over 6, just like we had over there. Okay, and then look for the cancellations again. These guys are gone, and then these guys have opposite sides, and they're gone. Now we have 1, 2, 3, 4 numbers that we're adding together. So we always have 4 numbers for n greater than or equal to 2. Question is, what's the pattern for the nth term? Once I know the pattern for the nth term, I know that that is the partial sum, the nth partial sum of this series. And if I take the limit of that partial sum, that nth partial sum as n goes to infinity, that's going to give me the sum of the series over here. Okay. What I like to do when I'm trying to do something like this is think about what is staying the same as we go from term to term. Let's see. The 2's never cancel. The 2 is always there. So that's staying the same. And then it doesn't hold for n equals 1, but for n greater than 1, we always have this 1 here. We're never going to get a 1 that cancels later on this list. There's never a way that you can plug in a value for n here where you're going to get a 1 for that second term, the negative 1. So we have the 2 and the plus a 1. And then these 2 other guys, they have negative 2's in the numerator, but the denominators change. So let's look at the pattern. Let's look for a relationship between these denominators and this subscript over here. When this is a 2, this denominator is a 3 and that one's a 4. When this is a 3, this denominator is a 4 and that denominator is a 5. When this is a 4, this denominator is a 5 and that one is a 6. So it looks like whatever this number is, this first number is one more than that. 2 goes to 3, 3 goes to 4, 4 goes to 5, so n should go to n plus 1. And then over here, this is 2 more than that number. So this is n, that's n plus 1, and that's n plus 2. N plus 1, and n plus 2. N plus 1, and n plus 2. And you should check and make sure that that works. If n is 4, n plus 1 is 5, n plus 2 is 6. If n is 3, well, 1 more than that is 4, 2 more than that is 5. If this is n, 1 more than that is n plus 1, 2 more than that is n plus 2. So that is our nth partial sum. The limit of that as s, or as n that goes to infinity, is the sum of our original series. So provided that that limit exists, and it does. The original series, which was this, which happens to be equal to this due to just algebra, partial fraction decomposition, is equal to the limit as n goes to infinity of s sub n, which is 2 plus 1, which is 3, minus 2 over n plus 1 minus 2 over n plus 2. And as n goes to infinity, this is 2 over a really large number. 2 over a really large number is a really small number, so that's going to go to 0. Similarly, that's going to go to 0. And the sum of the series, as n goes to infinity, the nth partial sum of the series will get closer and closer to 3. And so that is the limit that we are looking for. That is the nth partial sum, or that is the limit of the nth partial sum of the series, which means it's the sum of the series. So we'll go to WebAssign and we'll type in a 3 right there.